Welcome back to EasySpin Academy 2020. This is session number 5, and this session will be about coordinate frames, which is really important when you do solid-state EPR. So when you measure EPR in a solid sample, orientations play an important role. Molecules have fixed orientations, and within the molecules, the different interaction tensors also might have different orientations. So it matters how the sample is oriented in the spectrometer, and how the spin center is oriented in your sample, and how the tensors are oriented within your spin sample. So in this session, we're going to go over some of the basics of how EasySpin handles orientations. So we're not going to do any simulation, but just talk about the various tool functions that are there to support kind of thinking about and visualizing orientations. Okay, first of all, we need to talk about Euler angles. In order to specify the orientation between two different objects, there's several ways to specify that. And the one that EasySpin uses foremost is a triplet of Euler angles. And for example, let's take, actually let's go to the Euler angle documentation first. So if you go to the documentation, there is a documentation EPR reference. It's called rotations and Euler angles. So if you go there, you can see a summary of how EasySpin defines rotations. Euler angles are defined by 3 successive orientations around canonical directions that transform one coordinate frame, XYZ frame, to another. Okay, and this picture shows exactly how these angles are defined. These angles are called alpha, beta, and gamma, and in EasySpin, you should give them in radians and not in degrees. And these alpha, beta, gamma angles are then converted with an equation to a rotation matrix, which is a 3x3 matrix that specifies the angles between each pair of axes of the two coordinate frames. So let's go back. So let's define some angles. Let's say alpha is 20 degrees. We need to convert them to radians though. So one way to do that is just to multiply it by pi and divide it by 180. Or the alternative, which I'm going to write out here as well, is use degree to radian, which is a conversion function. Those two forms are fully equivalent. I tend to use the first form. Beta equals, let's take 40 degrees. Let's annotate this as these are radians. And gamma, let's take as an example 80 degrees. Now, in order to calculate the rotation matrix associated with these 3 Euler angles, you've used the function E-rot, where E stands for Euler rotation. So alpha, comma, beta, comma, gamma, and assign the result to R. If you run this and press Control Enter, and we not put a semicolon at the end of the line, we should get an output in the command window. And here it is. You can see you're getting a 3x3 matrix that contains values between -1 and +1 that are used to transform one frame to the other. So this is called a rotation matrix. Each element of this rotation matrix is actually the cosine of the angle between the two axes. So you have 2 frames. That's called the first frame A and the second frame B. If you take the arc cosine of R and convert it back to degrees just for easier looking at and run this, you can see that here, you can see that the angle between the x-axis of frame A, which is the first row here, and the x-axis of frame B, which is the first column, is 102 degrees. And the angle between the two z-axes is 40 degrees. Now, how are these rotation matrices used in EasySpin? So if you define a G-frame, right? We've defined a G-frame like this, cis.G-frame, and then you give 3 Euler angles. Okay, we're gonna just do this now without the cis. We're not gonna do any simulation. Let's call it G-frame. Let's put in some random values, maybe the same as before, 20, 40, 80, and convert that to radians. And then let's get the rotation matrix for the G tensor. Rg equals E-rot of the G-frame. And let's clear out. Actually, let's start with a new section, clear and clean the command window. Let's define a diagonal G tensor which is just, let's say, 2, 0, 0, 0, 2.1, 0, and 0, 0, 2.15. And now the transformed G-tensor is obtained by rotating the diagonal G-tensor with this rotation matrix. It's done by just Rg times the G diagonal times Rg transposed. So the dot prime or dot quote indicates or tells MATLAB to transpose the matrix, basically flip it around so the rows become columns and the columns become rows. Okay, let's clear out the comment window first. And now let's look at the output. The first output is the rotation matrix that is calculated from the Euler angles you give in G-frame. The second one is just a look at the actual diagonal G matrix with the X direction, the Y, and the Z direction of the G-tensor. And the third is now the rotated G-tensor, or transformed into that frame that corresponds to the Euler angles. And as you can see, it's still mostly diagonal. It has 2 point something on the diagonal, but it has small off-diagonal elements. Right? And this kind of tells you that the tensor is now rotated relative to the molecular reference frame. So this is how you transform a tensor. Let's say now you have given a rotation matrix. Let's call it R, right? I cleared it out, sorry. Let's get another, I'm gonna define a new R matrix. I'm gonna select all this code here and just run it by pressing F9, or on Mac it's Shift F7. So F9. Now we've got a new R matrix defined. You can now back calculate the Euler angles from the R rotation matrix by using a command called eulang. And if you feed that with R, I'm going to run this section again. Voila, you get back 3 numbers that are rough around the order of 1, but these are in radians. So we want to compute them back to degrees for better visualization. Multiply it by 180 and divide by pi. And voila, we can be getting our 20, 40, and 80 degrees back that we put in first. So this is how Euler angles work and how they relate to rotation matrices and how you can rotate a tensor. Or this is also how EasySpin internally rotates tensors. So for example, if you specify a spin system, let's say with G value 2, 2.05, 2.2, and say you also have a hyperfine tensor in there, let's say 10, 20, and 50. If you don't give any frame rotations, these two tensors are considered to be collinear. Now you could specify a tilt for, let's say, the A tensor. You would write A frame and then give some numbers here, and I'm just going to put in some random numbers. Okay, this will tell EasySpin that the hyperfine tensor coupling is actually rotated by the second Euler angle of a value of pi thirds relative to the molecular reference frame. So an important concept is in EasySpin is the molecular reference frame. So everything in the spin system is relating to that XYZ system, which you can just picture yourself however you want within the molecule, but it's fixed, right? And we have specified an A frame, which means the A tensor is tilted relative to that molecular frame. We have not specified a G frame, so which means the G is actually parallel or collinear with that frame. Basically, that's equivalent to saying sys.G frame equals 0, 0, 0. It means the same thing. If you don't give a G frame, it's assumed to be 0. So that's basically how these tensors are specified for a spin system. Now, this is all very abstract, right? Euler angles and rotation matrices are very math heavy, and it takes a while to actually make sense of them. For this, then now new in EasySpin 6, there's a rotation matrix viewer. And to get it started, let's take these 20, 40, 80 and call a function called rotview. And this function is only available if you downloaded the latest EasySpin 6.0 development version, which was published yesterday. So it's called 6.0.0/-dev26. So let's feed it some Euler angles. Actually, you don't have to feed it Euler angles. We can adjust them later. Let's run rotview. Rotview will fire up a small interface. It looks like this here. That allows you here in the bottom left to adjust the Euler angles. So you can change that, and we'll actually change the rotation, alpha, beta, and gamma. You can select the scenario you want to look at, either the G frame or A frame or D frame. Well, let's stick with it. Let's go to the A frame. And then it also allows you to show a tensor ellipsoid or not. Right? So let's look what it means. You can see here in dashed in red, green, and blue, the molecular reference frame, abbreviated with M. So XM is the x-axis of the molecular reference frame, and then we have YM and ZM. That's the first coordinate frame. The second coordinate frame is the frame of the tensor, of the in this case, the A tensor. The A tensor is kind of symbolized by this ellipsoid here, which kind of has three different lengths in each of the three axes. And you can see there its principal axis system shown in red, green, and blue. Red, again, is the x-axis of the A tensor. Then there's YA and ZA. And now basically you can visualize how this tensor is tilted relative to the molecular reference frame with these particular values of the Euler angles. And you can change them. And let's go back to a very simple case here. Let's say alpha and gamma 0 and beta is 20 degrees. So you can see that the molecular z-axis and the tensor z-axis are at an angle of 21 degrees here. Then on here on the top, you'll see a 3 by 3 array of numbers. These are the angles between the axes, as I've shown you before. So for example, the top, actually let's change the angles a little bit. So the top value here, which says 45 degrees right now, is the angle between the two x-axes. So between the molecular x-axis and the tensor x-axis. So that if you just measured the angle from here to here, it will be 45 degrees. So this is a little Euler angle and rotation matrix explorer that hopefully is very useful to understand this fairly complicated aspect of solid-state EPR a little better. This function is pretty new, and we still have some plans to improve it. So keep updating your EasySpin installation to get the latest for this function. So how are we doing time-wise? 10:22. We're good. Another new feature of EasySpin 6 is very useful if you are dealing with dipolar coupling tensors. For example, if you want to figure out the tensor for two electrons are coupled in space, or for an electron coupled to a proton. So I'm going to make a very simple example here. Let's say two electrons are exactly 1 nanometer apart, and they're apart from each other along the z-axis. So then the distance between those two electron spins is a vector, can be written as a vector, and if they're along the z-axis, both of them, then the x is 0, the y is 0, and the z is 1 nanometer. So this r is the vector that goes from one electron to the other electron. Now, if you want to get the dipolar coupling tensor, all you need to do is call a function called dip tensor. It stands for dip, for dipolar tensor. Then you first specify what's the first spin. It's an electron. And you need the second spin, it's also an electron, and then you have to specify the distance vector. Now, actually, let's clear and CLC at the beginning here. Voila, and then run this in the command window, and voila, it gives you the full dipolar coupling tensor. Now, if this were not an electron-electron coupling, but an electron-proton coupling, you just change one of the e's to 1h, and run that again, and see that you get couplings that are below 1 megahertz. The units that this gives back is always in megahertz. So that's another little utility function that allows you to calculate dipolar tensors. If your r vector, the connection vector between the two spins, is like tilted or points somewhere else, you can just enter that here. You just enter a slightly different vector. If you get the dipolar tensor, then it will have a 3 by 3 matrix where all the numbers are non-zero. There's a few other things that are useful to have with orientations. For example, a coordinate frame that's used often and very much in EPR are the polar coordinates. So where you have two angles, you specify the direction of a vector. And what you do is you just turn it down from the north pole, you take a vector that's pointing north, turn it down by a certain angle, and then I rotate it by a certain angle. This is equivalent to longitude and latitude on Earth. And you can convert the vector to angles and the angles to vectors using two functions that are called ang to vec and vec to ang. Okay, let's first start with the angles, right? Let's say phi is 10 degrees. As always, we have to convert to radians, the canonical angle unit in EasySpin, and theta is 30 degrees, so radians. Then if you can get the actual associated vector by just using ang to vec and then feeding it phi and theta, right? And so if you run this, let's clear the command window, and you're pressing Control Enter, voila, you get the vector that points exactly in that direction. And if you're gonna get a reverse, use the function vec to ang. Those are some basic things. I think the last thing I wanted to show in this demonstration is a utility that's useful for those of you who are doing crystal studies. So people who have samples that give spectra that depend on how you rotate your sample tube, right? And that applies to single crystals or also to oriented films. And EasySpin has, especially EasySpin 6, has now much improved capabilities to describe these samples. Underlying that is this whole mathematics about rotation matrices. So here's a utility function that helps you rotate something around a specific axis. So let's say we've got some frame. Where is my frame here? Okay, let's some initial frame orientation. I'm just copying that from my prepared script here. 3 Euler angles, right? 3 Euler angles specify a certain frame orientation. Okay, next we gonna define some rotation axis, and let's take the lab x-axis as rotation. EasySpin uses a fixed frame definition for the lab, and well, maybe I should show that right away. So if you go to the documentation and you go to the basics section of the user guide, there is one section called coordinate frames. That is quite important because it tells you how the various frames are defined, the convention for the frames in EasySpin. For example, there's the lab frame. What is the lab frame? That's the frame in your spectrometer, right? It has 3 vectors, the x and the y and the z. And it's of course a universal convention that the z-axis is defined to be along the static field. So if you have like a big magnet for an X-band EPR spectrometer, it points horizontally. I think also in the benchtop spectrometers, it points horizontally. And then if you have just a standard EPR machine, usually the oscillating microwave magnetic field goes vertically. And in EasySpin, that is treated as the x-axis of the laboratory frame. And this vertical axis is also the axis around which you typically turn your sample. That's your sample axis, right? And so, but there's crystal frames, molecular frame, tensor frames, and you can look up here in the documentation how they are defined, the word by convention, the x, y, and z direction for these quantities are. Okay, so let's go back. Let's define the x direction. 1, 0, 0. This is lab fixed x-axis, right? That's equal to the sample axis typically, right? In a standard spectrometer. And let's say it's specify a rotation angle like 20 degrees, again radians. And now if you basically want to rotate this frame specified by ORI 0 by this angle rho around this axis, for example, if you just do a single crystal experiment, what you do, you just say ORI equals rotate frame, and you feed the original orientation, Euler triplet, then the rotation axis, which is the x lab axis, and the rotation angle. Control Enter, and voila, you can see that it spits out the result of the rotation, again in the form of 3 Euler angles. So these are just some simple tools to handle orientations. Most of the times you don't have to use these tools directly if you just want to simulate something. But it's important to be aware of them, that they exist, and especially the new visualizer allows you to get a better feel of what these angles actually mean. So this concludes the session on orientation and coordinate frames. I encourage you to look in particular at the documentation. Just to reiterate, there's two places to look at. There is the coordinate frames section in the basics, and then there is a rotations and Euler angles section in the EPR, in the EPR reference part of the documentation. With that, I'll send you off to explore this or just take a break. We will be back for the last topic session of the day at 10:50, which is in 20 minutes. And see you there.